Hi, I'm Media Yousefi and welcome to my EUSIPCO paper presentation. In this work, we focus on audio-based toxic language classification using self-attentive convolutional neural network. This work was done during my summer internship at Microsoft Research. As we know, online social networking platforms are very popular nowadays. However, research shows that the interaction on these platforms naturally leads to hostility and aggressiveness. Therefore, it is desired to formulate a solution to control any toxic behavior that might happen on any of these platforms. Also, there's no standard definition for a toxic behavior, but generally it is defined as a behavior that intentionally disturbs other people's convenience, such as cyberbullying, cyber threats, and online harassment. Our motivation for this project is to reduce online negative behavior and also to facilitate the tedious work of human moderators. There are several benefits for audio-based toxic language detection. The first one is that there are many informative acoustic cues such as pitch, tone variation, and emotions that might be lost in a text transcription if we intend to use a text-based toxic language detection. And then the second one is that eliminating the transcription step, at least initially, may save time and computational cost. And the last benefit is to leverage the background non-speech information to capture the context of the conversation. Our proposed system for detection of toxicity consists of three main steps. In the first step, a CNN is used to extract higher level features from the input audio. Once the feature map is extracted, the second step, which is a feature summarization, is performed on the feature map to derive a feature vector, which is then passed to the classifier for the final decision. The main focus of this work is on the second step, which is the feature summarization. We propose to use several techniques to aggregate the information of the feature map into a feature vector. The first one is average pooling over time. The second one is learnable query attention. And the third proposed method is self-attention. Self-attention and learnable query attention tend to search for regions in the feature map which have higher levels of information and assign higher weights to those regions. Therefore, these approaches tend to perform a weighted average pooling over time compared to the baseline. In order to compare different proposed method, we conduct several experiments with the following network architecture. We use 4 convolutional layers to extract the features. Each convolutional layer has a kernel size of 5 by 5 with 32 channels. For the classifier, we use 2 fully connected layers, each with 256 neurons. We use ReLU and sigmoid activation functions and k-mean initialization. And our learning process is controlled by SGD optimizer. We use a batch size of 32, a learning rate of 0.01, and the patience for learning rate and early stopping is set to 2 and 4. And we decay the learning rate by 0.7 each time that we do not see any improvement in the cross-validation loss. And as you can see, the training loss and cross-validation loss tend to decrease over the epochs, which is a good sign. And it also manifests that the network has the generalization power to the examples that it hasn't seen during the training. For measuring the performance of the proposed system, we use several metrics such as accuracy, balanced accuracy, precision, recall, F-score. We have repeated the experiments multiple times and the average of results have been reported in this table. As we can see, self-attention outperforms the learnable query attention and the baseline across all different measures that we have. We have also presented the variance of the experiments, which is very low. It's around 1% across different metrics. This is a good sign because it shows that the network is reliable, and each time that we run the experiments, the initialization of the parameters is not going to have a huge impact on the final performance. We have also plotted the ROC and precision recall curves for the calculation of area under the curve. The dashed line is the random classifier, and as we can see here, the area under the curve for the self-attention mechanism is higher compared to the learnable query attention and the baseline. Which also manifests the improvement that self-attention achieves compared to the other two proposed systems. In this slide, we have visualized the features that we have extracted using the self-attentive CNN. So we are using two techniques, PCA and TSNE, for the visualization. And on the left side, we have visualized the input features, which are the log MEL filter banks. And on the right side, we have visualized the features that are extracted by the self-attentive CNN. As we can see, the log MEL filter bank features are not very suitable for detection of toxic language because they are not separable in the space. However, the higher level information that the self-attentive CNN extracts are more separable, therefore they are more suitable for the task of toxic language detection. To summarize, in this project, we focused on developing audio-based toxic language detection. We designed a meaningful, first-of-its-kind audio-based system for toxicity detection. We proposed two different attention mechanisms on top of the baseline. We showed how self-attention can capture the entire content of the utterance, which boosts the performance of the baseline classifier by 5% absolute improvement, resulting in 75.87% accuracy. We evaluated all proposed models on both a private and a public dataset. We studied the effect of data augmentation and the classification performance for both public and private dataset. Thank you very much for attending my presentation.